derivatives of higher order. So, in one dimension, in one variable calculus, you have function, you have first derivative, then derivative of the first derivative is second derivative, and so on. So, the idea is more or less the same. So, let us say, so E F are norm linear spaces, U contained in E is open, and F from U in E into F is a given map, and let us say A is a point in U, and now assume F is differentiable in a neighborhood of A. That means there exists an open set V such that A belongs to V and V is of course contained in U, and for every x in V, f dash x exists. Yeah, that is the difference between real and complex. Okay. So, in complex variables, if this happened, you would call it analytic function, but in real it is not true. We will see. Okay. So, this is only differentiable. Okay. In complex variables, when you say complex differentiable, then it automatically implies infinite differentiability, which is not true in reals. Okay. So, I am assuming that in a neighborhood I can differentiate this function at every point. Okay. So, now you look at this mapping f dash, which is from V contained in E, and what is the range? What is the range? It is L of E f, right? X goes to f dash of x. F dash of x is always a bounded linear operator. So, now I have a map which is in a smaller open set probably, okay, but the range space has changed now. Originally it was f. Do you really need this? No. Recording வேணுமா? சத்தம் ரொம்ப echo ஜாஸ்தியா. So, now the mapping goes in, this is the range space, it is a space of bounded linear operator, it is no longer f now. Original function went into f, then the derivative will go into LEF, and LEF is also a norm linear space. I have told you this because what is the natural norm in LEF? If you have any bounded linear transformation, the norm of T is sup norm Tx, norm x equal to 1, or any of the other three formulae I wrote for you the other. So, this is also a norm linear space. So, now you can ask me the question, is this function differentiable now? Okay. So, let if f dash is differentiable at A in B, we say f is twice differentiable at E. Okay. So, if f dash is differentiable at all points in V, we say f is twice differentiable on V, and so on. So, notation, so f double dashed of A is nothing but f dashed dashed
F is dependent on U.
uh,
F is prime dependent on U.
on V,
On V.
because anyway it is on a smaller neighborhood, the first derivative exists. So, where it exists only you can talk of second derivative. Okay. So, we are, it does not matter where, as long as the domain where the derivative exists, take like that. Okay. So, f double dashed of A is nothing but the first derivative of the first derivative of A. Now, where does this live? Where is this object sitting? Yeah, L of, it must be in L of something. E, very good. L of EF. Right? Whatever is on this side, it will be L from here to here. So, L of E of L of E of F. Okay. Suppose it is twice differentiable on V and the mapping x going to f double dashed of x. This is where from V into L of E to L of E f. If this is continuous, then you say f is twice continuously differentiable, and so on. So, now you know how to say. Now, this is a very inconvenient way of writing this space, because next I want to talk of third derivative, fourth derivative, how many times I will keep on writing L. Okay. It is not just because of that, but L of E of L of E of F is isomorphic to what is called L2 of EF. So, what is this space? L2 of EF is the space of continuous bilinear forms on E with values in F. Okay, so let us, what's a continuous bilinear form? So, you have E, okay, and a bilinear form is a function which is defined on E cross E, and it takes the values wherever it should take it. In this case, it takes it in F. So, A is a function of two variables now, U and V in E. What do I mean by continuous? This means that mod of U A of U V is less than or equal to some constant times norm U. Sorry, here it is norm. This norm is in F, these norms are in. This is what I mean by a continuous bilinear form. What is bilinear? That is obvious. It is linear in U and linear in V. So, A of alpha U1 plus beta U2 V is alpha times A U1 V plus beta times A U2 V, and similarly A of U alpha V1 plus beta V2 is alpha times A U V1 plus beta times A. So, linear in the first variable, linear in the second variable, then you call it bilinear. Trilinear, three variables, linear in each variable. N linear, function of n variables, linear in each variable. continuous means same thing, A of whatever should be less than some constant times the product of the norms of all the individuals. So, continuous trilinear form will look like what? A of UVW. So, it will be linear in U, linear in V, linear in W, and this should be less than M times norm U, norm V, and so on. So, you can now think of, and you can prove this exercise in linear algebra. If you have L of E of L of E of F, do it in finite dimensions, okay, as an exercise. Show that that's same as L2 of EF, namely it can be expressed. So, every member here can be written. Because if you take any H belong, say let us take any X belongs X and Y in E, and let us assume that let me call S is an element in L of E of L of E of F. Then S of X will belong to L of E of F, right? Now, therefore, I can act on it, act on some vector in E again. So, S of X acting on Y will belong to F, right? If X belongs to E, S of X will belong to L of EF. That means it is a bounded linear operator. So, S of X can be acted upon, can act on any vector Y, and that will give you finally an element in F. So, now you define the following thing: A of xy equal to S of X acting on. This is a bilinear form because it is linear in X, it is linear in Y, and then it is continuous because this is less than or equal to norm X Sx times norm Y, and that is less than or equal to norm S times norm X. No. Okay. So, given any element here, you can define an element here. Conversely, given any bilinear form, I can define something like this. So, it is 1-to-1 on-to continuous, and therefore, it is an isomorphism. Okay. So, every bilinear form, any element like this can be thought of to be a bilinear form. Okay. So, an application of the mean value theorem, I will not do that here. So, mean value theorem implies this bilinear form is symmetric. So, you can think of f double dash of A is a bilinear form. So, it will act on two vectors H and K, right? Right? And by symmetric I mean this is f double dash A K H for all vectors H and K, and this is a consequence of the mean value theorem. We will prove a particular case of this. This is the general theorem true in Banach spaces, and is one of the main big applications of mean value theorem which we stated yesterday. So, now let us take E to be Rn for this. And let us take F to be R. simple example. Okay. Then if I take a map f double dash of x, this is supposed to be a bilinear form acting on Rn. Now what is a bilinear form on Rn? How are they all generated? How do you produce a bilinear form on Rn? Good. And how do you produce inner products? Inner product is one example where it has some extra properties, but I just don't want that thing about positivity and such things for the moment. Okay. So in general, okay, even inner product, how will I produce different inner products in Rn? Huh? Yeah, that is the standard inner product, that is the dot product. Suppose I want some other new inner product, can you produce one? Huh? Voila, that is it. So I can write x transpose ay, which is same as sigma aij yj xi ij equals 1 to n. This is a bilinear form. It is linear in y, it is linear in x, and everything in finite dimensions of course is continuous, so you do not have to worry. So every bilinear form arises from a matrix, n by n matrix, okay, and this is the way you write a bilinear form. So if I say f double dash x should be a bilinear form, it must come from a matrix, okay, and it turns out that that matrix is precisely the matrix of what you call the second partial derivatives. So what did you recall what happened? F dash of x acting on any h, we said was I equals 1 to n df by dxi at x into hi, right? This is what we proved yesterday. This is how we introduced the notion of partial derivatives. Now if you iterate the same process, go to the next level, think of derivatives of f dash, okay. So sorry, f of x, no, f dash of x is fine, okay. Now I want f double dash of x, okay. So you can think of sigma d f dash by dxi x hi. Now this is again a linear operator, and this will further act on another k. And now f dash you write in terms of its partial derivatives, just as you did before, you will get the second partial derivatives. So f double dash of x acting on hk will be sigma d2f by dxi dxj x hi kj. Okay, so this is how, and this matrix is called the Hessian matrix. Hessian is nothing but the matrix consisting whose ijth entry is the ijth second partial derivative of a given function. Now I was not very careful, I do not even know if what I written is correct here, namely I simply wrote hi kj, maybe it is hj ki, it is possible, but I do not have to worry because of this fact. If since this bilinear form is symmetric, this matrix will also be symmetric, so it does not matter in what order I write this. Okay. So let us try to now prove, at least in this case, that that matrix is symmetric. So is it clear how this second order partial derivatives come? The second, because the second derivative is a bilinear form, and bilinear forms on Rn are nothing but matrix products, okay, and therefore So I'll do it in R2 and f from u in R2. So I am doing a very, very particular case of the general case, which is so assume df by dx, df by dy exist at all points it's enough if they exist in a neighborhood of a particular point, but I don't care. I mean, I just prove it. I'll work with that neighborhood, that's all. So I am assuming that they exist at all points. 2 d2f by dx dy exists at x naught y naught in u and is continuous at x naught. Sorry, exists in u and is continuous at x naught. Okay, it should exist somewhere, it is a function and that function is continuous at x naught y naught. Then d2f by dy dx x naught y naught exists and d2f by dy dx at x naught y naught is the same as d2f by dx dy. So if the first partial derivatives exist, well, they have to, otherwise you can't talk of the second derivative. Okay, the first partial derivatives exist, second partial derivative also, one of the second partial derivatives exists, okay, then and is continuous at a particular point. So wherever it is continuous, at those points the other partial derivative will also exist and they will be the same. So you have symmetry, that matrix of second derivatives is a symmetric matrix. So choose a square neighborhood of x naught y naught contained in U. So this is U is there, x naught y naught is some point, and I am picking up a square which is inside. So choose hk such that mod h mod k are less than 1/2 side of the square. So that x naught plus h, y naught plus k belongs to the square. Okay. So x naught y naught is at the center of that square, and I am taking increments such that for all x naught plus h, y naught plus k, they are still inside that square. Okay, that's all I am. It's okay to do this because ultimately what am I going to do? I am going to take h going to 0, k going to 0 jointly or in iterated form or something like that. So I am only interested in small values of h and k. So It is this is no, this is not unreasonable assumption. So you make this. So define A of hk to be f of x naught plus h y naught plus k minus f of x naught plus h y naught minus f of x naught y naught plus k plus f of x naught y naught. And for y near y0, near meaning such that it is in, or everything is inside that square, okay. Define psi of y equals f of x naught plus h y minus f of x naught. Then what is AHK? It is psi of y naught plus k minus psi of y. Psi of y naught plus k is f of x naught plus h y naught plus k minus f of x naught y naught plus k, that is here. Psi of y naught is f of x naught plus h y naught minus f of x naught y. So all four terms are taken care of. So now I am going to use this hypothesis, df by dy exists. So that implies psi is differentiable. What is psi dash of y? It is df by dy at x naught plus h y minus df by dy at x naught. I am just differentiating this with respect to y, so that is just the partial derivative. So now we apply, we are now in one dimension now. This is a function of a one variable only. So you know I can apply the classical mean value theorem. Okay, if I wanted to prove this theorem in full generality, I will have to use the other mean value theorem which I proved, okay, and make an estimation. But now I will use the classical mean value theorem because I am only in a one dimensional situation. So AHK equals psi of y naught k, y naught plus k minus psi of y naught, and so that can be written as k times psi dash y naught plus theta 1 k, where 0 is less than theta 1 k. That is the usual mean value theorem. Namely, the difference between 2 points can be written as the length of the interval times the derivative at some intermediary point. Intermediary point between y naught and y naught plus k I am designating as y naught plus theta 1 k, where theta 1 is between 0. So that if you expand it out, this is what df by dy x naught plus h y naught plus theta 1 k minus df by dy at x naught y naught plus theta 1, because I am using the formula for side. Now, what is my next assumption? That d2f by dx dy exists. That means I can differentiate this once more with respect to x, okay, and then again I will apply the mean value theorem. So, d2f by dx dy exists, and mean value theorem implies that this is equal to k times. Now I am applying differentiating with respect to x. So, the length of that interval is h. So, k times h times, and I have to differentiate this function with respect to x. So, that is d2f by dx dy at some intermediary point, which is x naught plus some theta 2h y naught plus theta 1. Agreed? I have applied mean value theorem 2 times. So, I have, and I have used so far this hypothesis, I have used this hypothesis. I still have not used this hypothesis and the continuity. I will come to. So, if h and k are not 0, I can write a h k by h times k equals d2f by dx dy at x naught plus theta 2h y naught plus theta 1. So, call this relation. So, for x near x0, define phi of x equals f of x y naught plus k minus f of x y naught. Again, a of hk equals phi of x naught plus h minus phi of x, right, same 4 terms. Now I am grouping differently, that is all. So, let me look at a h k by h k. I will write this as 1 by k times phi of x naught plus h minus phi of x naught by h. Now, if I take the limit as h tends to 0, will this limit exist? It is nothing but phi dashed of x, which exists because df by dx exists. Okay. So, df by dx exists implies that phi is differential. Therefore, for k not 0, limit h tending to 0, AHK by K H equals 1 by K phi dash at x naught. Right? And what is phi dash at x naught? This is equal to df by dx at x naught y naught plus k minus df by dx at x y x naught y divided. Okay. Leave this aside, go back here and now take the iterated limit here. So, AHK by HK limit as h tends to 0, limit as k tends to 0. So, now I am going to use the last hypothesis, namely the d2 by dx dy is continuous. So, this will be limit as k tends to 0 of d2f by dx dy. I am going to let h tend to 0 and this is a continuous function. So, I will get x naught y naught plus theta 1. And again this is a continuous function. So, as k tends to 0, I will get d2f at x y at x naught y naught. So, the iterated limit of AHK by HK exists and is equal to this. Now, go back here. I have already taken limit h tending to 0. So, now if I take limit k tending to 0, I know it exists because I have already proved it. Okay. So, limit, so this is equal to limit k tending to 0 of whatever is left there, df by dx x naught y naught plus k minus df by dx at x naught y naught divided by k. So, this limit exists and is equal to this, but what happens if this limit exists? What is it equal to? This is nothing but d2f by dy dx at x naught. So, this is that limit and it should be equal to this. So, that is the conclusion of the theorem. d2f by dy dx exists and it is equal to it. So, just using mean value theorem and using the fact that the second derivative of one second derivative is continuous, you deduce that the other second derivative exists and is equal to this. Okay. So, this matrix d2f by dxi dxj is a symmetric matrix always. So, matrix of second derivatives is a symmetric matrix. Let us look at this example. take f of x y equal to xy into x square minus y square by x square plus y square if xy is not 0 0 and 0 xy. Okay. So what about fx and fy? Well, elsewhere, if it's not the origin, fx and fy exist. You can differentiate. Okay, you can write out what the derivative is. At the origin, what do you have to do? If you want to find the first derivative, partial derivative along x at the origin, this is the line y equal to 0. So you put y equals 0 and then differentiate the resulting function, which is a function of x. If I put y equals 0, I will get 0. So that it's a 0 function, so it is 0. Similarly, here I want the y derivative, partial derivative at the origin. So I put x equals 0. I again get the 0 function, so this is equal to 0. And fx fy exists other places. I will give you the formula, you can check it. It is just some calculation with the quotient rule. So you get x power 4 minus y power 4 y plus 4x squared y cubed divided by x square plus y square the whole square, and fy is x power 4 minus y power 4 times x minus 4x cubed y square x square plus y square. So now let me take f x y at 0 0. That means I must take fy, take the function fy and then put y equals to 0 and then differentiate it as a function of x. So let me take fy and then put y equal to 0. So I get x power 5 by x power 4, which is x. So I will get 1. Put y equal to 0 here, you get a function of x, differentiate it with respect to x and evaluate it at the origin, but that this function is just x, so the derivative is always 1. What is f of xy at 0 0? Thank you. Yx. So I have to take fx, put x equal to 0 and make it as a function of y, and so if I put x equals 0, I get minus y power 5 by y power 4, which will give me minus y, I get minus 1. So what is wrong, or nothing is wrong? Just now I proved a theorem. Yeah, so if you take the second derivative, either of these you differentiate, everywhere else they will agree, you will get the same function, but it is not continuous at the origin. So that not continuous at the origin reflects in the fact that these two are not equal. Okay, so the theorem why I am saying all this is I used all the hypotheses to prove that theorem, and I want to tell you that those hypotheses are all necessary. Okay. Of course, fx and fy have to exist, otherwise there is no point talking of second derivative. So, that you can't do away with. Then at least one second partial derivative must exist, otherwise we are not going to talk about the second one. But so the only only extra hypothesis which is not natural is the continuity hypothesis. That was the only new hypothesis we made. Everything else you have to make. Now, this example shows you have to make that hypothesis also, because without that continuity you do not get the symmetry of the derivatives. Okay, so from now on, let's just so you have u or some neighborhood of A or whatever, and assume that f double dashed x exists at all points. So, where this goes to L2 of EF, which I said is isomorphic L of E of L of E. So, now I can ask you, is the second derivative differentiable? If it is, then you call it f triple dash. If it exists, where will it belong? It will belong to L of E of L of E of L of E of f. So, this is L3 of EF, that means all trilinear forms. Okay. So, f triple dash A will act on 3 ways, HKL or the HK, you know what, UVW. So, it will be linear in each of these, and it will be bounded by some constant times norm U, norm V. Again, by the mean value theorem, one can show that this is a symmetric trilinear form. That means you have any permutation of u, v and w, u, right? The value will be the same. So, in the case of Rn to R, so you will get all the partial derivatives dxi, dxj, dxk. Okay, ijk may be repeated. 3. Yeah. So, if you permute these in any order, it won't change. So, that will be similar theorem to what we just now proved, provided you make all the necessary continuity assumptions. Now, you can define the nth derivative. By induction. Suppose f n minus 1 exists. Okay. So, f n minus 1 will be a function from u contained in E going to L n minus 1 EF. That means the n minus 1 linear forms. Okay. And then you can, if fn minus 1 is differentiable at A, then its derivative is the nth derivative at A. And where will it belong? It will belong to ln of E. okay, belong to Ln. So, it is a n linear form, it is a function of n variables. So, it has to act on n variables and then and Fn is a symmetric n linear. That means Fn of A at A acting on n variables, right. So, U1 or H1, Hn, this is equal to Fn of A acting on H sigma 1 H sigma n for all sigma in the symmetric group Sn, that is the group of permutations of n symbols. Okay. Take any permutation of this thing, the value will not change. Again, this is a consequence of the mean value theorem. And as I said before, if you make the appropriate continuity assumptions, then all the usual partial derivatives which you define, nth order partial derivatives, you can write it in any order. So, this is how you define for all orders the derivatives. So, once you have defined derivatives of all orders, then you can talk of Taylor expansion. So, I will give you the statements, I will not prove any of them. So, F U containing E to F, assume F is n minus 1 times differentiable in U, F is n times differentiable at A. So, in the whole neighborhood it is differentiable n minus 1 times, and at a particular point it is differentiable one more time, okay, n times. Then norm of f of A plus h minus f of A minus f dash A acting on h plus minus 1 by 2 factorial f double dash A. Now, it should act on two variables. So, h minus 1 by n factorial Fn of A acting on Hn. This is little o of norm h. That means, if you divide this by h power n, it will go to 0 as h goes to 0. So, what does that symbol mean? Fna Hn is Fna which should act on n variables. So, it will act, this is n times. So, I am repeating the same things. When n equals 1, that means when all this, if you suppress, that is just the definition of the derivative. That is how we define the Cauchy derivative. Okay. So, this is natural that you have this. Each time you are thinking something, it is one more time differentiable. So, it is second one is the mean value theorem. So f compute contained in U. When f, assume f is n plus 1 times differentiable in U, assume norm f n plus 1 at x is less than equal to m for all x. So what is the norm of a multilinear form? You know, when it is continuous, so if A is a multilinear form, it's a function of n variables. Then if you say it's continuous, this is less than equal to some m times norm x1, norm x2, norm x. Okay? Then you say norm of A is the smallest possible m which you can have. So this is the sup of norm of A x1 xn by norm x1 over all x which is not 0. Okay. So that's called the norm, just like the norm of a linear transformation, norm of bilinear forms. Then norm of f of A plus h minus f of A minus f dash A h minus 1 by 2 factorial f double dash A h h minus 1 by n factorial fn of A at h power n is less than or equal to m times norm h to the n plus 1 by n plus 1. Okay. So if you compare this result and compare with this, what does this result tell you? This says if you divide the left hand side by norm h power n, it will go to 0 as h goes to 0. That's all it says. This one tells you how fast it goes to 0. If I divide by norm h power n, it goes as fast as norm h. It will give you a more precise order of convergence. Okay, it tells you, gives you a estimate, very precise estimate of the error term. This just says error goes to 0, and that tells you how big that error is, how fast that error will go to 0. So this is a much more precise theorem than this one, but you pay a much higher price. Look at the hypothesis. I only needed f is n minus 1 times differentiable and n times differentiable at one point. Here I want n plus 1 times differentiable everywhere, and that the norm is bounded. Okay, so I am asking a lot of conditions on the function compared to the previous one, and by if I pay more I get better answer, that's all. To state the third one, you will need to know what is meant by. So suppose I have a function f, say from 0 1 into a Banach space. What's a Banach space? It's a complete norm-linear space. Okay, norm-linear space, the metric is complete. Then what does this mean? What is the meaning of this? What is it first? What do you think it is? What? Huh? Is this what is this object? Is it a number? Is it? It's a number. Let's say any other suggestions? So it's still a number, right? It's an element of, correct. So it's an element of E. So it's not a number. Okay, this is all these. So think of integration. What is integration? It's a limit of a sum. So this also is a limit of some sum. Hopefully, sum of vectors is still a vector. So the limit of a vector must also be a vector only. Okay, so this is a vector Y belonging to E. How do you define this vector? Of course, you can think of Riemann sums and try to pass to the limit, etc. But the general definition, this is called the Bachner integral. For a continuous function, it does not matter, you can do it. Okay. Y equals 0 to 1 f of t dt is a vector in E such that for all phi in E prime, what is E prime? E prime is the dual space. Dual space means continuous linear functionals on E. Okay. For all y phi in E prime, phi of y, now this is a number because y is a vector and phi is a continuous linear functional, and therefore this is a scalar now. Okay. This is equal to integral 0 to 1 phi of f ft is a vector, again phi is a linear functional, so phi of f of t is a number. So t going to phi of f of t is a mapping from real numbers to real numbers. So then I know what I mean by integration. So this is the integration of a real valued function, so it has meaning. So this is a number, this is a number, and this should be true for every continuous linear function. That is the definition of the integral. Now the question is, does it exist? So every time given a function, you have to check. For continuous functions, one can prove it exists, okay, using what is called the Hahn-Banach theorem in functional analysis. For others also you can prove, okay, so various classes. So you can have develop a complete integration theory for various functions which are from the reals into a vector space. Okay, so why do I make such a definition? At least let us be, I am not going to show you that it exists, but why will I expect this to be true? Again, we go back to the notion that integral should be really a limit of a sum. So if I take a finite sum and apply, say, let us say y1, y1, then phi of this will be sigma phi of yi, right. Now I am saying integral is some limit of such sums. So if phi is a continuous linear functional, then the limit phi of the limit must be limit of the phi, okay, because that is property of continuous functions. So that is why we require that this is true. Now at least one thing, but there may be many vectors which obey this, that is not possible by the, again by the Hahn-Banach theorem in functional analysis, which says that if you have a vector which satisfies this property, then that y is unique. So you can't have two different integrals. So okay, integral will be uniquely defined. Just as the derivative was uniquely defined, integral is also uniquely defined. So this is called, this is how you have to understand the integration of a vector valued function. what you do is the integral is the unique vector which satisfies this for every continuous linear function. Okay. Now, in some special cases you can actually define what is that integral, like if it is a continuous function, then you take a partition and then take Riemann sums, pass to the limit, etc. You will be able to prove something. It is going to be very messy, but you will prove it. Okay. Now, suppose if Fe is Rn, for instance, then if phi is a function from 0, 1 to Rn, then what is it? Phi of t will be some n functions. So, phi 1 t, phi n of t, right? Because it is a function in Rn, so each coordinate you write. Then the integral is easy. Integral of phi t dt will be just the integral of the each coordinate. It is a vector in Rn, and it will automatically, you can check, satisfies that condition. Okay. So, if you are only interested in Rn, then this is not a big deal, it is just a coordinate integration. So, now let me state the third form of the Taylor expansion theorem. So, f is from U contained in E. F. So, now you are seeing E is a nonlinear space and F is Banach. And F is continuously n plus 1 times differentiable. In U. So, now I am paying much more. Look at the mean value theorem statement. I needed f to be n plus 1 times differentiable and its norm should be bounded. But now I am saying it is n plus 1 times continuously differentiable. So, the derivatives must be continuous. So, that is the extra requirement I am asking. And originally I said E and F are only nonlinear spaces. Now I am claiming I want F to be a Banach space. So, I am asking it to be complete also. Okay.
The difference between n plus 1 times differentiable and n plus 1 times continuous differentiable.
Yeah. So you take x and look at this map fn plus 1x. If this exists for all x, you say it is n plus 1 times differentiable. Okay. Now this is a map from where x is in U contained in E. It is going to Ln plus 1 EF, which is also a nonlinear space. Okay. Now, so you have a mapping x going to Fn plus 1x. If this map is continuous, then you say that it is continuously differentiable.
The bounded and continuity are not same.
No, boundedness, unless you have some compactness built in, you cannot expect continuous functions to be bounded. Okay, boundedness is different from continuous. Oh, unless, yes, a bounded n linear form is a continuous n linear. Okay, like, okay, but the norm need not be bounded. Okay, so in that case you are right. Just as I said, a linear transformation is continuous if and only it is bounded. but that bounded has a different meaning from bounded which, and yeah, that's true. So continuously n plus 1 times differentiable means that this mapping is continuous. So then f of a plus h equals f of a plus h f dash a, sorry, f dash a h plus 1 by 2 f double dash a h h plus etc. plus 1 by n factorial f n a h n, and now I must obviously get a more precise statement than before. So the first statement only said the error term goes to 0. Second term said the error term goes to 0 like norm h. Its size is h power n plus 1. Okay. Now I am going to tell you exactly what the error term is. Okay. So it is equal to integral 0 to 1 1 minus t power n by n factorial f n plus 1 a plus th to the n plus 1. This means I am applying this vector n plus 1. Sorry, something is wrong here. Sorry, no. Apply it here, h power n. N factor. So this gives you exactly what is missing. Okay, so this gives you the error term very precisely, but then you are asking for a lot of now if you take n equals 1, so you want f is okay continuously differentiable. N equals 0. Okay. So it is 1 times continuously differentiable. So f of a plus h minus f of a equals integral 0 to 1 of f dash a plus th h. And this is a special case of the Taylor thing, but this is nothing but the fundamental theorem of calculus, because if I take d by dt of f of a plus th, what will I get? I first, by chain rule which we did yesterday, I get f dash at a plus th, and then I have to differentiate this with respect to t, I will get h. Okay. Now if I integrate both sides from 0 to 1, this is the derivative evaluated, is nothing but the function evaluated at the end points. So if I put t equals 1, I get f of a plus h, and t equals 0, I get f. So this zeroth order Taylor expansion is nothing but the fundamental theorem of calculus. Now the funny thing about all these so what does the Taylor expansion tell you? It says that f of a plus h equals f of a plus f dash a h plus 1 by n factorial fn a h power n plus little o of norm h. That was the first thing, Taylor expansion I got. So if f is sufficiently differentiable, Taylor expansion exists and the coefficients are precisely given to you. I mean, they have only this. But let us take this E equals F equals real line. A function may have a Taylor expansion, but still it may not even be differentiable sufficiently. Okay. So let us take this example. So take f of x equals x cubed sine 1 by x, and this is okay. Then mod fx is equal to mod x cubed, right? So f of is little o of mod x squared. Okay, because if I divide by x square and let x go to 0, it goes to 0. So I can write f of x equals 0 plus 0 times x plus little o of mod x. Okay, right? Fx is little o of mod x square. I write it like this. It's a trivial Taylor expansion I write, but it does not satisfy the hypothesis of the Taylor expansion theorem, because the second derivative of this function does not exist at the origin. You can differentiate it once, but you can't differentiate it twice at the origin. So even though the second derivative does not exist at the origin, in spite of that you have. So these are some funny things which happen in but if the function admits enough derivatives, then the Taylor expansion always exists and the coefficients are uniquely determined by these fn a by n factorial and so on. They are the only possible coefficients. Okay, you can't have any other coefficient. Another example where a function may be C infinity, but it does not have a Taylor expansion at all. Okay. So fx equals e power minus 1 over x square. X is not, if x is positive, and 0 if x is. So claim f is C infinity. You only have to worry about the origin. On this side of the origin, it's e power minus 1 by x square, which you can differentiate n number of times. On the other side, everything is 0. So the derivative function, everything is 0, all orders. So the trouble comes only at the origin. And so you have to check that the function is continuous, differentiable, etc. at the origin. So from the left hand side, everything is 0, the limit. So you have to take the limit from the right hand side of the function and all its derivatives as x tends to 0, and then check if it goes to 0. Now if you take this function and all its derivatives, they will be of some combination of terms like x power k e power minus 1 by x for various values of k. Okay. Then by L'Hopital's rule, you can show that as x goes to 0, all of these terms go to 0. So it's exercise for you to check that at 0, the limit from the right will also be 0 always. Okay. So you try to write down the derivatives of this one and then take the limit as x tends to 0, you will get 0. Okay. So that is L'Hopital's rule. So this is a C infinity function, and all derivatives at the origin are 0. So then this function does not have a Taylor expansion, because if a function is differentiable and it has a Taylor expansion, then I told you what are the coefficients. Okay, the coefficients must be, if I write f of a plus h, this will be sigma f of a plus f dash a times h plus f double dash a h square by 2 factorial plus and so on. So only these coefficients must be there. So if you have a f of x, if you put at 0, so this will be f of 0 plus f dash 0 at x plus f double dash 0 x squared by 2 factorial and so on. This will be the Taylor expansion. But for this function, all the derivatives are 0. So you will get 0, 0, 0, 0, everything is 0, but f is not a 0 function. It's a non-zero function. So this function is an example of a function which is C infinity, but which does not have a Taylor expansion at the origin. Okay. So in complex case, we started today with the discussion. If you had a function which is differentiable at a point, complex differentiable, then all derivatives exist, it's not only, and it has a Taylor expansion in a neighborhood. Okay. So it becomes analytic, that's what we call analytic. So in the real functions, you have a distinction between real analytic functions and C infinity functions. A real analytic function is a C infinity function which has a Taylor expansion. Okay. But so like sin x, cos x, all these are real analytic functions. But a function like this is a C infinity function, but it does not have a Taylor expansion. So it is not analytic. Okay. So real analytic, so in the real variable case, you have an extra class. So C infinity and real analytic are not one and the same. So if you have a C infinity function, we cannot blindly write the Maclaurin series or Taylor expansion and so on. You have to prove it. Okay. Whereas in the complex thing, you can do it automatically. Okay, I will stop with that. And so this afternoon, I will prove for you the 1 minute implicit